it reached to the certain level. Okay, let me just copy. Okay, this is one of the example lah, that you can just set your options to be displayed and also iter. I just copy this one. Too lazy to. Okay, it's basically not this one. Okay. Okay, so I've defined the option to be an option set of display the iteration. Now if I just use back this root finding, and then I just have to put options at the back. Okay, there you go. Then it will start to give you it will display the iteration that it takes, each iteration that it takes in order for you to get what is the root of the equation. And then it also mentioned you whether it use an initial the interpolation or the bisection method, because this one is a predefined function, so it just works on its own. So now inside the book, they also have a way to do the bisection method. So there is a MATLAB function there that explains how to develop the program in order to find the roots using a bisection method. So what it did was just it applied the bisection method that we have with the different iteration. So for each iteration, you will have that you will try to find XR, which is equals to lower limit plus upper limit divided by 2. And then if and then it will test if like the function of XL with respect to the function of XR. If the test is less than 0, then X upper is basically going to be your the new XR. The XR will be the new XU, and if the test is actually more than 0, and then the XL will be the XR. This one is basically the same as what we have here, bisection method, right? Is basically this thing, the condition that you have to follow. If the FXL multiplied by FXR is less than 0, then the root should lies between the first subinterval. So you need to have your XU now replace your XR now become the new XU. So it's basically the same thing. So you can just go through this one, or okay, if you want to use this one, since I have already imported from the M file, so I can just call upon the function bisection. So if I want to use a bisection here, how do I okay? So a function of so I can put a root is equals to bisection, bisection, and then it should have the function. Yeah. Let me just specify the function first. Function equals to function of x x to the power of 3 minus 7, and then if I want root is equals to bisection and bisection, and then you can just include the function, the lower limit, the upper limit. You can also specify the error tolerance, the maximum iteration, things like that lah, because it is already inside the function itself. Okay, so bisection, I could have my function is known as the function. My upper limit or your lower limit is 0. let's say my upper limit is 5. Let's say I want the maximum iteration is 50. Even if I don't put any maximum iteration here, they already have a default maximum iteration, which is going to be 50. So let's say I do 150, let's say I put 30 is my maximum lah. And then just have to press, and then it will try to calculate, and it will pull out the root is equals to 2.1875. Huh. It's weird. 1.75. One 1.9. I keep getting a different answer. I need to check back on this one. Maybe there's something wrong here. But that one is okay. That one is one of the way to do it. Also, you can also develop your own program to do the bisection method. This one is this one is the one that I've been working on. It's basically a fairly simple one. So because you need to understand understand how the bisection works, you can actually derive the coding in order to do as how we are going to do it manually lah. So first thing you need to have the function. Okay, in this case I just put it as an input, so you need to input your own function, and then you need to put your lower boundaries and also the upper boundaries, and then you can do a check first. So you do a check if the function of xl multiplied by function of xu is more than 0, which means that they are both in the same quadrant lah. If fxl is negative and fxu is also negative, and we have a positive value which is more than 0, then you just have to tell you that there is no root exists within the given interval. If not, the start calculation lah. For iteration, this one I set the maximum iteration to 100. And then if you remember, bisection method is just it cut into half. So xr is equals to xl plus xu divided by 2. And then if the fxl multiplied with fxr is less than 0, then xu become the new xr become the new xu. So if not, it become the xr become the new xl. And then to set it to terminate the equation, if the absolute value of fxl is less than 0.001, which is nearly 0 lah. Put it 0.01. If it's nearly 0, it will just end the iteration there.
Doctor.
Yeah.
Here, can we say like if absolute value of xl equals to 0? Like, can we assign that?
Yeah, you can also. Let's say if you want to put equals to 0, it's also okay. But then you need because you see that with the iteration method that bisection is going on, because it cut into half. Now, since your interval becomes smaller, even if cut it into half, it becomes even more smaller. So then your interval is still going to be there. It's hard for you to directly get into an exactly 0 value. So that's why we put it as 0. Less than 0.001, 0.0001 is also okay. In order to make the calculation more simpler. If not, it will keep on iterating until it gets exactly to 0 point. Okay?
Thank you, Doctor.
Okay. Now, if I want to use this one, since this one is a bit different than that one in a way that I can already call bisection 2. And then it will ask you, because in that case you need to input it in form of the function itself. In this one is I ask to put it input based on input lah. So you need to input the function, you need to input the lower limit and also the upper limit. So let's say the same function that we have just now. I should have it somewhere here. So function. So you have a function of x, and then the same thing 0, then upper limit is 5. So it will tell you the root is 1.9, and the number of iteration that it takes is 12 iteration. So basically, there are a few ways that you can do even though it's basically the same thing, is to find the root. Even in the same method, like bisection method, you could have a different way of writing the coding in order to get to the same answers. This one is basically, I think, the same with F0 that we have. Where's my F0? Okay. Yeah, the value here is basically the same lah, 1.9129 and also 1.9129284. So that's about it about the MATLAB. Yes, do you guys have MATLAB?
Yes, doctor.
If you have MATLAB, you can, because I see that from other section, I think some of them have problem accessing the license or anything through the official UTM license. If you could have your own MATLAB, then it's also okay. If you don't really have it, you can also use Octave. Yeah, Octave Online. Octave Online is you can use it online, so you don't really need any kind of license for it. So I think because I tried to use the same function that I use in MATLAB, the same system that I have. So I tried to input it into the Octave Online, and it does work. It could work also. So no problem there. The only thing is you just have to register with the Octave, but basically it's just from Google account or anything, so already okay. So it's basically the same thing. I could call the bisection in here. I call it bisection, and then it asks you to enter the function. The function is this. The value of xl is 0 and 5, and then you get the same thing. And you can also use, because I tried just now, you can also use the F0 here. Maybe you need a little bit of time for calculation because this one is online, but it does get you to the values that you need lah. So basically, if you don't really have MATLAB, you can also use the Octave Online. Okay. Now, any question here before we proceed to the next topic? Or any question regarding chapter 2 overall?
Doctor.
No? Yeah.
For this function, if we use the absolute value of fxl, if we use instead fxr, will it give the same answer?
Yeah, it should be, because you can choose fxl or fxr is fairly close to 0, then it's okay. Because once you start breaking it into section by section, because fxu and fxl the xu and xl will become closer and closer together. So I think once this fxl reaches near 0, I think fxu on the same hand should also reach to 0 also. Yeah. But that one works for bisection method. Because in others, then you need to think lah. Because this one is somehow logical thinking. So let's say if you have a false position, where you false position also work in the same way lah. Once you cut it short, it should be closer to the 0 as well. Okay. Next, we'll move on to the next chapter lah. Okay, the next chapter that we are having here is the optimization. So the objective for this chapter is to locate an optimum value of a single variable function with the golden section search and also parabolic interpolation. So we have just two methods here. golden section search, and also the parabolic interpolation method. And this one is to locate the optimum. So in the last chapter, we try to locate the root. The root is just to I have any slide that I can open. This one. Can open it, then I can just write it down, which is easier. Okay, this is the one. Okay. Just need to say, this will be okay. Now, in the last chapter, we are trying to find roots. Okay. In this chapter, we are trying to find the optimum value. Okay, what is the difference? Is basically if you have a parabolic, say something like this, or you have something that goes up and down, up. So if you want to find the root, you are trying to find the value of x that makes the function of x equals to 0. So this one is x, and let's say this one is a function of x. So for the last chapter, we are trying to find this point. Now, for this chapter, what we are trying to find is to find the optimum value. The optimum value could be either a maximum, or it could also be a minimum. So you are trying to find the optimum value here. Either it's a maximum here, or this one continues downwards, or it's a minimum here. So that is what we are trying to find in this chapter. So for the chapter, locate the optimum from a single variable function. So this one works better in this chapter. We're just looking for a unimodal function. So it's just a single variable function. It's not going to be a multi variable function. Okay, I don't think we are going to take a look at the several variable function because I think the objective for this class is to focus more on the single variable function, and then to recognize the trade-off among the approaches with particular attention to initial guesses and convergence. Okay. Okay, so now the first one is going to be the interaction optimization. So optimization is a process of creating something that is effective as possible. Optimization is, if you look in the aspect of numerical method, is going to be finding the minimum and also the maximum. But in general, as an engineer, there are more to think rather than maximum and minimum. Optimization is always with the amount of information that you have, with the limited supply that you have, you are trying to make the best of a system. That one is what we call an optimization. So as an engineer, you are always going to be confronting optimization to balance up the performance and also the limitation. So you want to get the most performance with the limitation that you could have. If you could have, let's say, you just have, let's say you need to heat up something, but then you just have a limited amount of steam that you can use, then you need to optimize the system to make it as high temperature as possible with the amount of steam that you have. You could do that by having a more controlled flow rather than having more flow. You can optimize the flow to be slower flow. In a way, you can get more heating going into the system. So those are the kinds of optimization that you might face as an engineer. So from a mathematical perspective, Optimization is finding the maximum and minimum lah. So the goal is to determine the value of the variable that yield maximum or minimum function. So basically what you want to do is you want to find the value of x that makes the maximum or the minimum function of x. Okay. So optimization, one-dimensional problem involve a function that is depend on a single variable. If you have a multiple variable, it's called a multi-dimensional problem lah. Optimization for the multi-dimensional problem. We will be taking mostly into consideration mostly for the one-dimensional problem. So we just have a function that depends only on a single variable. So it will be a function of x, not really the function of x and y. If you have a moving x and also moving y, it would have some sort like this lah. So both of the x and also y would influence the how the graph would form. Whereas for a single variable function, it's going to be like a 2D things, just one line going up or going down. Okay, so we also have the global optimum and also the local optimum. It is what it sounds like. Global maximum and global optimum is basically the very best solution for the whole case. Whereas the local maximum and minimum is for the neighboring case lah. So you have a smaller section that you just focus on that section only to see the maximum and minimum of that particular section. Whereas the global one, you need to see the whole length of the values. Okay, one-dimensional unconstrained. Okay, we will take a look at the golden section search. Okay, so the search algorithm is to find the minimum between the interval xl and xu with a single minimum. So you need to understand for the golden section search, you need only a unimodal interval and also with just a single minimum. You could not have two minimums in the interval. If you have two, then the golden section search wouldn't really work. You need just to have one minimum or one maximum. So I'll try to explain it with a minimum examples, and then basically maximum is just the reverse of the minimum lah. And then it uses the golden ratio pi to determine the location of the two interior points x1 and x2. So using the golden ratio, you will reduce one part of the graph in the section lah. So the formula of pi is actually 1 plus square root of 5 over 2, which is 1.618. And then so basically the step to find with the golden section search is you need to have the x1 and also x2. The formula is x low plus d is equals to x1, x2 is equals to xu minus d. So d here is equals to the golden rule here. The same here, the golden ratio minus with 1 multiply with xu minus xl. And then you have to decide. This one is basically somehow similar to the bisection method. You need to decide which one to discard. So to decide which one to discard is you're just comparing the fx1 with fx2. So if fx1 is lower than fx2, then you will discard whatever is bigger than x2. Or if the fx2 is lower than fx1, you will discard whatever is lower than x1. So if you see from the figure, what you will do is if you have a minimum here, and then you have your xl at the end at this beginning, and then xu at this end, and then first thing first, you need to find x1 and x2. So x1 is basically from xl, you plus with d, and then you get the x1, and x2 is xu minus with d. So you have two new values lah, and then you compare the fx of x1 and x2, and then you will see which one is lower. So if in this case, the x1 is lower than x2, so if x1 is lower than x2, and then you have to eliminate whatever is whatever is below than the x2. So now your x2 will become the new XL. Okay, let me just show you in this thing. Okay, so let's talk about the golden section search. So okay, so how I'll try to explain on how does the golden section search you how to do it lah. So basically what you will have is some sort of graph. Okay, and then let's say you have I'm going to explain it in terms of minimum. Okay, you have this kind of graph. So you have a minimum going to be somewhere here. So this is the point that you want to find. Okay. Okay. Let me draw it more nicely. Okay. So you have a graph that goes down and then goes up. So now, let's say you start your values here with, let's say we take here, this one is your XL. And let's say we take here is your XU. Okay. Now, from XL and also XU, the first step is you need to find, the theory behind it is you need to find there is a new x1 and x2. So this x1 and x2, the distance for x1 and x2 is going to be let's say I have a red color here. So from XL, okay, from XL you will find x1. Okay, no, from XL you find x2. From XU you find x1. So is it? Yes. Okay, from okay, x1 is from XL, x2 is from XU. Okay, from XL here, you will find x1. So, and then this one is x1. And then from XU, you will find x2. Okay. Like this. From XU, you will find this XL, x1. And then this one is going to be your x1. And then x1 is from XL. You know. Sorry, I keep getting it confused. It's a little bit tricky, but it's not really that hard lah. Okay, now this one is actually x1. For this one is from XU, you will find x2. Okay, now the ratio between the x1, So the golden ratio here is actually equals to, first thing that you need to understand is, to make it easy to understand, okay, the length for x1, the red length here, the distance between the distance between the x2 and xu is actually equals to the distance between the xl and also x1. This one and this one is actually the same distance. Okay, and then the ratio between the distance of the xl with respect to the okay, this ratio is the golden ratio. Okay, this one is equals to because in the formula it's actually going to be 1 minus 5 minus 1 lah. So this one is actually equals 0.618 something, 0.618. Okay, so from here that you know, this one is going to be x1 minus with xl, whereas the bottom part here is going to be xu minus xl, and then equals to this ratio here. And then if you try to rearrange, that's how you get x1 is equals to xl plus with the 5 times with xu minus xl. Okay, the same thing could be said for the red line here. So the red line here is actually also equals to the red line is actually equals to xu minus with x2 divided with xu minus xl. So that's how you get your x2 equals to, if I rearrange it, it's going to be, it is going to be this one here, this one pick up 5 times with xu minus xl, and then just have to bring the x2, xu minus x2, no, x2 minus x2. You got the x2 xu minus with this one. So that's how you actually get to this value lah, x1 and x2. That's how we get to this equation. So it's basically the golden section method is from the ratio between these lines. Okay, so and then what do you have to do next? Now, and then once you already have x1 and x2, you will try to compare. You will try to compare the fx, the fx1 and also the fx2. So this one is the fx2. Okay, so now you get your fx2. Fx2 is bigger than fx1. So what you want is actually to have it in the, you know that the minimum is going to be the one which has lower lah. So the one which has lower value is going to contain the minimum. Since this one here is higher than the fx1, so what you can do is you can actually remove this part. So what you do is you actually remove this part. Okay, this whole part lah, you already remove. So what you are going to be left with is actually, if I were to draw it again, including the part that you have already removed, it is going to be something like this. And then now it's just from here until here. So this is going to be your new XL, and then this is going to be your new XU. Now, from XL and XU, you need to find the X1 and X2 again. And then you also need to find the FX1 and also the FX2 in order to compare it again. So the step is to compare these things and to eliminate it. That's what we do in the bisection method. Okay. It's okay. I think when you start doing the examples, it will be much more clearer. Okay, and that for finding the minimum is fx1 is less than fx2, then the x2 become the xn, and also the x1 now becomes the x2. And then if fx2 is smaller than fx1, then your x1 now becomes your xu, and your x2 now becomes your x1. Okay. For the error, the relative error for golden section search is a bit different than other normal relative error that we calculate. Because normally you just have to calculate with the difference of the present value minus with the past value divided by the present value multiplied by 100. So in this case, it's going to be 2 minus 5. This pi here is actually 1.6 something. 1.618 and then you multiply it with xu minus xl over the optimum x. This one is the new x that you are going to find. Okay, let's do together example 3.1. So to use the golden section search to find the minimum of the x squared over 10 minus 2 sine x. Okay, so they gave you the interval between x1 is equals to 0 and xl is equals to 0 and xu is equals to 4. Okay, okay. I want to just start doing it together. You can start doing it first, and then we'll try to discuss if there is any issues. Okay.
Okay, dokter.
Okay, so this is the, let me just make it bigger. Okay, so this is the step of to do the golden section search. You can refer back to this one. But do you have the question? Okay. Just jot down the question first, and if you have already ready, then I'll just proceed to show you the steps that you need to take.
Doctor, the value of phi is 1.6, yeah?
Yeah, the value of phi, you can just take it as 1.618.
All right, thanks.
Okay. Okay, I will also start writing here, and then we can just discuss it together lah. So now it was given to us that the function of x is equals to x squared over 10 minus 2 sine x. Okay, and it also gives us the x low is equals to 0 and x upper is equals to 4. Okay, so let's start with iteration number 1. Iteration number 1, first thing that you need to find is you need to find the b. The first thing that you need to find is d. So d, the formula is the golden ratio minus with 1. And then you have your xu minus with xn. Okay. And then this one 0.618 multiply with 4 minus with 0. You should get here some 2.472. Okay, and then you will have your x1 and also you will have your x2. So x1 and x2, x1 is lower plus with d, and then this one is upper minus with d. Basically very straightforward. This one is 0 plus with 2.472. This one is 4 minus with 2.472. Okay. Then what you could get is this one is 2.472, and this one is actually 1.528. Okay. Next thing that you have to do is find the function of x1 and also find the function of x2. So this one and this one is basically so this one is 2.472 square minus over 10 minus with 2 sine 2.472, and this one on the other hand is going to be 1.528 square over 10 minus 2 sine 1.528. Okay. Anybody has any value already?
Doctor, for fx1 is minus 0.63.
0.63.
And the other one is minus 1.765.
1.765. Okay. So now, so minus 1. Okay. Now we know that this one is actually smaller number. So since this one is actually smaller number, we know our fx2 is less than fx1. Okay. Therefore, what will happen is from the slide, it mentions that if fx2 is lower than fx1, then your x2 become xf. Okay. Your x2 now become your xf, and your x1 now become x2, or it's the other way around. X2 now becomes x1. sorry, x okay. Since fx2 is less than fx1, then xl x1. The x1 here becomes the new xu, and then the x2 now becomes the new x1. What does that mean? The x, this one 1.528 now become x2. Our x2 here is the x optimum. X optimum in this range lah, which is equals to 1.528. Okay. Now from here, you need to, because in this case you need to find the EA. EA is basically, since this one is different, is 2 minus with pi. Pi here is 1.618. 2 minus 5 multiply with the upper minus the lower over the optimum. So that's why we have an optimum here. The optimum that we have in this range is 1.528, and then multiply by 100. So 2 minus with 1.8 multiply with 4 divided by 0.5. Yeah, you get 100. Okay, yeah, that makes sense. So you get, for the first iteration, since there is nothing else, you get 100% error. Okay, now what do? Is we proceed to the next iteration. The next iteration is actually iteration 2. For iteration 2, so we have already, you need to find the new D lah. So now D is still equals to for iteration 2, you know that your XU from previously, the X1 now becomes the new X2. The X1 now becomes the new XU. So this X1, 2.472, becomes the new XU. So XU here is equals to 2.472, and then your XL is still the same lah. Your XL is still going to be 0. Okay. Now you need to find back the D. D is equals to 0.618 multiply with 2.472 minus with 0. This one is equals to 1.528. Okay. And then basically you repeat back the same step. Your x1 is equals to the xl plus with d, and your x2 is equals to your xu minus with d. So this one and this one is equals to 0 plus 1.528, and this one is 2.472 minus with 1.528. Okay, and if you calculate 2.472 minus with 1.2 minus with 1.528. So here you get minus oh, that's why I thought it was weird. Supposed to be 2. 2.47. 0.5. 0.944. Okay, this one is actually 0.944 and this one is 1.528. Okay, the same thing, you need to find the function of x1 and also the function of x2. Just have to plug back the numbers into the formula that we have. The formula is this one is 1.528 square divided by 10 minus with 2 sine 1.528. And then this one is 0.944 square over 10 minus with 2 sine 0.944. Okay, from the solution that I have, this one is actually minus 1.765 and this one is minus 1.531. Okay, so we know that now the fx1 is less than fx2. So your x2 becomes the xl. And then your x optimum is equals to 1.528. 1.528. Okay. Your error is equals to 2 minus 1.618. Multiply with the upper and lower limit. We have already said that the upper limit is going to be 2.472 minus with 0 divided with 1.528 and then multiply with 100. This should yield a 61.8%. Okay. Up until now, okay?
Yes, doctor, yes.
Everyone else okay?
Okay, doktor.
Okay, doktor.
Okay, ah. Tak okay tadi nak panggil nama dah. Okay. This one I think is fairly simple. So and then after that, what you need to do is you need to continue with the iteration number 3, iteration number 4 until you get the. In this question it doesn't mention anything. Yeah, in this question it doesn't mention where you need to stop. In the solution, it gives until the 8th iteration, the EA is less than 5%. Okay, so you guys can just continue doing this. And you also have exercise 3.1 and 3.2. Okay.
Doctor,
Yeah.
so if in the question it doesn't mention the error, for example, like error minimum is 5%, so we just assume that after we touch 5%, then we can stop the calculation or what, doctor?
I think basically generally in for your examination it should give you a stopping criteria or it should give you how many iteration that you should have to. Because if not, then it's the rule of thumb is 5%. 5% is like the usual values that we can take, which is fairly normal. But then I think in examination, especially in examination you should have been given some sort of error criteria to stop. If it's not given, then just ask. Or because if it's given the significant figure, you need to understand from chapter 1 I already mentioned that there is a a way to find the error tolerance if they give you the number of significant figures that they want. Okay. So, golden section method. I guess that one is all about the golden section method. Next one is already the parabolic interpolation. I didn't plan to go for parabolic interpolation today. We're just taking a look at the golden section method. So, any question about the golden section method? Is it confusing? Okay, of course it's not. Because that one is for the finding minimum, and if you want to find the maximum, okay, if you want to find the maximum, it's going to be the other way around lah. It's basically the same thing, it's just the other way around. Now, for a minimum, you know that it's going to be like this. For a maximum, it is going to be something like this. Now, for a minimum, if you find, let's say, if I'm not talking about XU and XL, I'm just talking about X1 and X2 lah. Okay, let's say lah, after you calculate, you get X1 and X2 here. So now this one is your fx1, and this one is going to be your fx2. Okay. So if fx1 is in this case fx2 is lower than fx1, so we are going to use the second one lah. So if fx2 is lower than fx1, what you have is actually you know that the root is going to be in this region lah. So you know that the region before the fx1 is not going to be, it is not going to be influencing the minimum. So minimum will not fall in between this region. So that's why we have eliminated this region, and then your x1 now becomes your new xl. So previously you have some sort of xl here and some sort of xu here, and then you find x1 and also x2. So if fx1 is lower, is higher than fx2, anything below the x1 is not going to have the minimum. So that's how we can just eliminate the values below the x1, and then the x1 now becomes the new xf. So and then you have to find again your xl with xu. Okay, and then if it's a maximum, you need to understand. Okay, just give me a minute to think about it. Yeah. Okay. Because XL. Okay, let me explain it again. I wanted to explain it again since let me just explain from the beginning again, just to make sure that you guys doesn't want to go away. Okay. It's okay. So now you have a function here with a minimum. So you have a minimum, and then you start with XL and also XU lah. XL, and then you start with XU times XU. Okay. And then you have XL and XU, and from XL you get X1, and then from XU you get X2. Okay, and then from here you try to find out like what is this fx2, and this one is fx1. fx1. So you have fx2 and fx1. You need to compare. In this case, our fx1 is less than fx2. Why? So you guys can hear me, right? It's just my PowerPoint is somehow is become unresponsive for a while. Okay. And then when we have fx1 is lower than fx2, then your x2 becomes your xl. You see, fx1 is lower than fx2. So you know that this is the region that you will have your minimum is going to be somewhere here. So your x2 now x2 become the xl. So xl now is going to be shifting to the x2. So what you did is basically you just remove this part, and then this x2 now becomes the new xl. Okay, that one is for the minimum, and for the maximum one is basically the opposite of it lah. So you have the same thing. You will also have the x2. You will also have the xl, and also here you have the xu, and then from xl you find your x1, and then this one you got your x2. So basically the same thing that you try to do is you try to find your what is your fx2, and you also try to find, let's say lah, this case is going to be fx1 and also fx2. Okay, so in this case your fx1 is more than fx2. Okay, if your fx1 is more than fx2, then you know that if maximum you want it to be at the higher range. You don't want it to be at the lower range. So what you'll do is you will remove whatever is having a lower function of x value. So what you do is you remove this part. Your xl now is going to become your new xu. Your x2 now will become your xl. The xl. Is that clear? How does the to finding the minimum and maximum just changes the which one that you want to remove, which part to remove. So basically, if you want to find the minimum, you will try to remove whatever part that have the higher fx value. And if you want to find the maximum, you will try to remove whatever part that have the minimum value. Is that clear? Any question? Okay. If you have no question,
Doctor, can you share the slide in the
yeah,
group?
of course.
Okay, thank you, Doctor.
No, it doesn't want to go away. Okay. I will be there. Yep. Of course, I will be there. Okay. It's okay. So I need you guys just to do exercise 3.1 and also exercise 3.2. I'll just upload this one and these things into the uh, e-learning, and then you guys can just do exercise 3.1 and exercise 3.2. Make it as a tutorial, and then just I'll open also a submission now. So before next class, you can just do exercise 3.1 and exercise 3.2, and then just submit to the e-learning. Okay. And in the next class, we will take a look at okay. Okay, I also need to give a tutorial for the MATLAB one lah. Because they just to make you guys familiar with writing MATLAB function for the I'll give a question, just a simple question. I want you guys to just get familiarized with how to develop the MATLAB coding for the problem that you are facing lah. If you that one, I'll try to give by tonight. Just another tutorial. It's basically going to be a simple question on the probably second method or Newton-Raphson method. You can just use if you have the book, you can refer to the book. One way to do the Newton-Raphson method is already in the book. If you want to develop your own style of coding the MATLAB, is also very good. Or you can find from the internet also how other people try to develop the MATLAB for the Newton-Raphson method and also the second method. Okay, if you because that one will be for the MATLAB one. What is important is that you know how to develop the function. It's not about getting the end product there. End product is also important, such that it is a correct answer. But it also affects you on how you try to convert from a known procedure to do the let's say Newton-Raphson method. You need to convert it into a coding that the language of the system that it could be able to iterate the equation effectively. Okay, that one I'll try to give it by tonight. And for this tutorial is going to be exercise 3.2 and also exercise 3.1. Okay. I'll try to just clean up this one first and then put it into the e-learning. So you guys can just check it there. The attendance, I think I already posted it in the e-learning. Yeah, the attendance is already there. Please go ahead and scan the attendance. I'll be closing it around 1 o'clock. So
Doctor, can
up
I
until
ask
now,
a
I only have
question?
26 people who signed the attendance. Please, if you haven't do it, just go ahead and do it.
Doctor, can I ask a question?
Yes.
In our test or exam, do we need to show the MATLAB application or we just write it manually? Do we have questions like that?
I don't think in the last few semester, I don't think you have to develop a MATLAB inside the examination. The MATLAB function and the utilization of MATLAB, I think mostly is going to be the assignment and the project lah. Not really going to be in the examination. Examination is mostly you have to just do manual calculation.
Okay. Thank you,
Okay.
Doctor.
All right. Any other question?
And doctor, regarding the test,
Mm-hmm.
as you can see, the questions, it is very lengthy. Some of them, it takes time. Will there be enough time, or just
Okay. In test, we'll try because test you cannot just give a direct question like this lah. This one is fairly very simple. Like you have a t square minus 8t plus 12. This one is fairly direct because in test one you need to somehow be a little bit more challenging. Like this one is basically for tutorial case for you guys to exposure you guys to the to start doing the step and everything is fairly simple lah. But in the test, sometimes it will have to be maybe a real problem base, maybe something that you can relate numerical method to. Let's say if you see from the book or something, there are problems related to parachute diving in. There's momentum there. Some of the things that you need to try to because you are going to be a chemical engineers, and we need to expand your vision not only towards solving the problem like from a mathematical method, but how to apply it in a chemical engineering environment. So sometimes the examination question is going to be somehow it's going to be a little bit tricky. There are some question that is going to be lengthy. There are some question that is going to be not directly straightforward, but the basic for the calculation and everything will take into consideration. So we won't if the solution is fairly lengthy to get the convergence, then maybe we'll specify it that you need to just do a few iterations. Or maybe we want you to compare between the two methods. So let's say we want you to compare between the bisection method and also the force position method. So we cannot expect you guys to just remember the tutorial that we did last time that have like 35 iteration, then only you can get to an answer. So we could not really give those kind of question that you need to find it in 35 iteration. Then maybe we just ask you for one at each and every one, just do 4 iteration. So we will try to limit it with the amount of time that students have lah. So don't worry about that. That one is for us to figure it out. But if we find out the solution is a bit tricky, but it's manageable in that time, we will give it also lah. So the time that you need to take to figure that one out, you will have to figure it out quickly lah. Okay.
all right? Thank you, Alex.
All right. Any other question? Yeah.
Doctor, when is the tutorial due?
Before next class. Next class is on Sunday, so you have weekend to do. Is it okay?
Okay, thank you, doctor.
Doctor,
Alright.
the MATLAB that you have done in like can you send the MATLAB file in the chat, right? Because I want to refer that to do some questions.
Okay. You want the MATLAB that I've done, Okay.
Yeah,
No
yeah,
problem.
this one, the file that you have been shared. Yeah, thank you.
Okay. Where's my chat area? This is the chat area. Oh, sorry. I sometimes I miss out about the chat thingy. Because when I do a full screen thingy, it does not really shows whether the chat is coming in. Sometimes it shows at the top right hand, and sometimes I just missed that one. Okay, any other question? Question about anything is also okay. No problem, since we have a little bit more time.
Doctor.
Yeah.
Regarding the MATLAB, can we use the coding to solve Newton-Raphson as well? Because we only have bisection
okay.
and also
The MATLAB that I just gave just now, because I developed it based on the bisection method. Because if it's a Newton-Raphson method, then you need to know, because Newton-Raphson method works with the function divided by the differentiation of the function. So you need to input the function, and so you need to input the differentiation of the function. Or if you can find the MATLAB formula to do the differentiation, then you can just input that one together. If not, you can just put it as a differentiation function. And then for the formula, you need to rearrange it to satisfy how the Newton-Raphson do the calculation. Because this one is based on the bisection method, the Newton-Raphson one will be different.
all right. So I mean I can still use this this form to just need to modify it to suit the Newton-Raphson, right?
Yeah, can. But this one also you see, because I just this one is just a one-liner. If you have, because if you see this one, it just mentioned that what is the root and what is the number of iteration. But you can also find this one is the implication of MATLAB. You should have already learned it, how to put it into a table. I would prefer it to have it into a table form. In order, like, it's easier lah, because in examination and everything you need to finalize the answer in a table form, some sort like something like this lah. You always will have to finalize your answer in a table form. So you have your lower limit, your upper limit. If a bisection method, you need to have your XR, and then your function of XL and XU, or function of XL and XR, and then you need to have your error. So usually it's this okay, for the golden section search, you need to have all those kind of things. So from XL and XU, you need to find X1 and X2, and then for the function of fx1 and fx2, and then also the D lah. D could be at the front, so it's okay, no problem. And then finally also the error. Okay?
Okay, all right.
Alright. Any more question? I still can't really remove this. I have no idea why. Oh, no, I don't want to draw some weird, like a permanent marker or something. I'll figure it out. No worries, and then I'll upload it into the e-learning. So while we are still here, any more question? I'll try also to upload this slide. Yeah, I need to upload the slide. And also for this case, also we will have to do the MATLAB for the more, let's say for the golden section method. You'll also have to do the MATLAB function for this one. You can also see inside this, or if you have the book, you can also see in the book on how they develop the or the function. You need to try to understand what's the meaning of all those values that all those characters that you put in, usually you have some sort of implication to the system. Okay, if there is no more question, thank you guys for joining to the class. I think there's nothing else that I would also want to say. Just I'll upload this one into the e-learning. You just have to do this tutorial, and also I want to give another tutorial on the second method or the Newton-Raphson method, so that you can just do it in MATLAB. So just try play around with the MATLAB. If you don't have the MATLAB, I've shown you. You can also use OCAD online. In the tutorial for the one that I want you to use the MATLAB, I also want you to send me the M file, and also just paste the screenshot of the answer that you get into the assignment that you write. Okay. All right. If nothing else, thank you very much. You can dismiss.